Unit 2, Lesson 8 is derivative of the inverse of a function indirectly. The reason it's indirectly is we're looking for a relationship here. A lot of times you're given information where you can't find the inverse, and then therefore you can't find the derivative of that inverse. So this is a relationship College Board wants you to know. And I guess it can be useful. So we're going to indirectly find the derivative of the inverse of a function. This is kind of the background presentation and kind of why it works. There's an additional part 2 where we have a couple of examples. So hopefully you know how to find the inverse of a function, how to sketch the inverse of a function, or at least a relationship between the two inverse graphs, and know corresponding points of inverses. So like I said, a lot of times you're not going to be able to find the equation of an inverse because, well, you're given something where the inverse isn't a function. And a lot of times it's easier to find the derivative of the inverse indirectly anyways, as long as you understand a relationship. So G is the inverse of F. We're going to fill out the table, or at least I am, and then we're going to graph F and G together on the same set of axes. So when x equals 0, F is 2, or we could say F of 0 is 2, which makes G of 2 equal to 0. I like that in blue. And F of 1 is 4, so G of 4 is 1. F of 2 is 6, so G of 6 is 2. And so on down the line. A function and its inverse have all the same ordered pairs, just with the x and y reversed. Or, the x for F is the y for G, and the y for F is the x for G. So if we graphed those two on the same set of axes, and I asked Desmos to do that, I asked very politely, we can see there's some nice symmetry. When inverses are graphed, we see those graphs reflected across the line y equals x. And then the other thing you'll notice is if we connect ordered pairs and kind of count off slopes, average rate of change, that sort of thing, we can see, for this red one, F, change in y is 2, change in x is 1, change in y is 2, change in x is 1. And when we swap x and y to go to G, the inverse of F, change in x is 2 and change in y is 1. So of course that makes sense, and that's really the relationship we're looking at. So how could we find an equation for F? Well, we can see that, maybe I can get black, that won't annoy me. That's not quite black, but whatever. Right, change in x is 1, change in x is 1, change in x is 1, change in y is 2, change in y is 2, change in y is 2. So it's pretty obvious F is linear since we see a constant rate of change, 2 over 1, 2 over 1, 2 over 1, so a slope of 2, and then we notice that 0.02 is going to give us our y-intercept. You could do it in a different form, this is just kind of easiest. So in terms of G, we could count off the slope, but we don't have to, because we already know 2 to 4 is a change in 2, 4 to 6 is a change in 2. And so it's really a relationship between this slope 2 on F and the slope on G. And since we're changing x's for y's, you could also think of that as, well, in slope, we think of that as change in y over change in x. So the slope in the inverse is the change in the old x over the change in the old y. And hopefully you have no problem finding that y-intercept of -1. You can see this x value, if we continue backwards, prior 6, 4, 2, 0, and this y value would be -1. So I'm just going to try to hammer home this point about swapping x's and y's allows us to figure out a relationship. And the x-intercept of F is where the y value is 0. So that's -1. 2 times -1 is -2, plus 2 is 0. And then instead of asking about f, I'm going to ask about the y-intercept of g, because these two functions are inverses. So if we swap x and y, well, we're kind of talking about the same point. We're talking about a corresponding point. So the y-intercept of g, that's when x is 0. So 1/2 of 0 minus 1 is -1. So the y-intercept of g is 0, -1. The x-intercept of f is -1, 0. And that's, of course, depending on how you look at it, the same point, just transformed from one function to its inverse. The y-intercept of f is where x equals 0. That's, of course, 0, 2. And you can guess what the x-intercept of g is, 2, 0, because, again, we're changing x's and y's from a function to its inverse. And you can check to see that's correct. 1/2 of 2 is 1. 1 minus 1 is 0. That's indeed the the x-intercept of g. So if we're going to do slope of a tangent line, it's probably best to go slope of a secant line. We're much better at that sort of stuff from algebra skills. So slope of a secant line on f between 2 and 3, the best way to write that is f of 3 minus f of 2 over 3 minus 2. And if you flip back a couple of slides, or if you're writing them down, f of 3 is 8, f of 2 is 6, so 8 minus 6 over 3 minus 2. My title in class was write but do not simplify, because really students think this too matters, but it doesn't. We're looking at a relationship. So what's the slope of the secant line of g? Lost a word, between 6 and 8, and so that's, of course, g of 8 minus g of 6 over 8 minus 6. And if you look back, g of 8 is 3 and g of 6 is 2. So what we see is the slope between 2 points, as long as those are the same corresponding points. Since we're changing x's and y's, and maybe we want to look right here in the middle, this is the best place to see it. Right? In f, 8 minus 6 is the change in y, and in g, 8 minus 6 is the change in x. In f, 3 minus 2 is the change in x, and in g, 3 minus 2 is the change in y. And so it's kind of knowable. If you knew the slope of f, you could figure out the slope of g between those same corresponding points. So if you've forgotten how to find inverses, the best way or the easiest way, or the way I was taught, replace x with y, replace each y with x, and then resolve for y. So 2x minus 2 becomes x equals 2y plus 2, and we'll subtract 2 from both sides, divide by 2, and y is equal to 1/2 x minus 1, which is, of course, the other function we've been working with. So if we swap x and y here, x equals 1/2 y minus 1. Ideally, we're going to get back to y equals 2x plus 2. And I guess we're going to add 1 to both sides, and then multiply both sides of our equation by 2, and y equals 2x plus 2. So you might think that proves 2x plus 2 and 1/2 x minus 1 are inverse functions. It doesn't prove it, it shows it, I don't know. So in order to prove two functions are inverses, and you need to know this because we're going to use this definition in order to find derivatives in a moment here. Two functions are inverses if and only if we compose them. F of g of x is equal to x, and g of f of x is equal to x. So let me show you what that means, or maybe not what it means, but I'll show you how to do that. So here we're going to start out with f of something is 2 times something plus 2. Don't think of x as x. Think of x as a place to put other things. And in this case, we're going to put g of x here inside of f. And we don't want to write g of x here, 2 times g of x. We're going to write what g of x is equal to, 1/2 x minus 1. So if we simplify, hopefully we'll get down to x, and of course we will, because 2 times half of x is x, 2 times -1 is -2, and then we can simplify -2 plus 2. And so, well, maybe we should take a step back before we do that. Earlier we had, I think it was g of 8 is equal to 3, which makes f of 3 equal to 8. I'm just going to try to explain this f of g of x stuff. So what this says is f of g of x should be equal to x. So in our case, f of, just with this ordered pair, and hopefully it'll illustrate the point, f of g of 8 should be equal to 8, and of course it is, because g of 8 is equal to 3, and f of 3 is equal to 8. And so all this says is this f of g of x stuff. We're going to put an x into g. We take that y value, and that y value is the input to f. And if we get the x we started with, then we have a pair of inverses. And that's kind of the exact same idea, just in algebraic form, as swapping x and y. So we compose g with f, and we think of that as g of stuff as 1/2 stuff minus 1. On the left, we'll write literally f of x, and on the right-hand side in this blank, we're going to do 2x plus 2. 1/2 of 2x is x, 1/2 of 2 is 1, and then that 1 minus 1 becomes x. So now we can say, okay, f and g are inverses. We knew it already, this just counts as proof. I think I'll attach these so you can play around. So this is not this, obviously these aren't lines. This is just meant to represent, hey, some function, f of x in red, and some function, g of x in blue. And hopefully you notice 0, 1, 1, 0. We're talking about corresponding points. And the idea here is that this change in x on f is the exact same numerical value as this change in y. So these two slopes, the slope of the secant line of f between 0 and 2.5, and the slope of the secant line on g between 1 and 5.656, whatever that is, are simply reciprocals, because the change in y and the change in x have flip-flop numerator-denominator. If we get those points closer together, this still holds, right? This change in x from 1 to 2.46 is this change in y from 1 to 2.46. And I don't need to show you both of them, I hope, for you to realize, oh yeah, of course these slopes are related. The slope on the red graph between 0 and 1.3 is the reciprocal slope on the blue graph from 1 to 2.46. Look, they're even closer. What do you think is the relationship between the slopes of these two secant lines? They're, of course, reciprocals. And notice now we're getting to, okay, well, what about the slopes of the tangent lines? And so we could say this slope on the red one is f prime of 1. And this slope on the blue one is not f, g prime of 2. And so the relationship still holds that these two slopes are reciprocals. But notice the tangent slope of f at 1 and the tangent slope of g at 2 are reciprocals. And, well, this 2, this y value in f is the place where the inverse g is going to have the reciprocal slope. That's the corresponding point. And that's why it's confusing. I probably didn't say that as well as I could. Confusing meaning f prime of 1 is the reciprocal slope of g prime of 2, not g prime of 1, right? It's not at the same x value, it's the corresponding x value, which happens to be, the y value in f. So how would we find the tangent slope to f at f is x squared? That's, of course, f prime is 2x. How could we find that specific one at x equals 2? F prime of 2 is 4. So importantly, we're going to need in a second here the fact that f of 2 is equal to 4, right? If I put 2 into f, I get the y value 4. So maybe I should do these in a backwards order, but that's okay. It's already here. Write an expression to find the tangent slope of g, and that's of course 1 over 2 root x, g prime. And then you might think I'm asking you to find the tangent slope of g at 4 by putting 4 in here, but I'm not. I'm asking you to think about this relationship. Okay, and so while we have that here, the tangent slope of g at 4 is 1/4. Why? Well, g prime of 4 is 1 over f prime of 2. That's this idea we had here. Right? So maybe explain a little bit more. F of 2 is 4. G of 4 is 2. Right? Hopefully you feel like squaring and the square root are inverse functions, and they're perfect inverses for positive inputs. So I'm well aware of that part. Anyways, so what we know is the slope of f at 2 and the slope of g at 4 are going to be reciprocals. Okay, so the easiest way to show that or to prove that is using this definition of inverses. So we're going to use the chain rule to find the derivative of f of g of x is equal to x and g of f of x is equal to x. So you can see g is the input to f, so we're going to do the derivative of f is f prime, still with the same input g, times the derivative of g. Or if you're in your my class, the derivative of f of something is f prime of that same something. That something is g, which has a rate of change g prime of x. The derivative of x is 1. So in this case, because I'm trying to illustrate what's going on here, we're going to solve for g prime in both cases. So g prime is this bit, and we'll divide both sides by f prime, which happens to have an input of g of x. And I'm trying to show you that it doesn't matter whether you do f of g or g of f. So here, the derivative of g of something is g prime of that same something. That something is f of x, which has a rate of change of f prime. Derivative of x is 1. So here, we divide by f prime. And notice, we don't get the exact same visual bit, but we do get the exact same idea that g prime and f prime are reciprocals, or the slope of g somewhere is the reciprocal slope of f somewhere. But remember, these actually do convey the exact same information, because this is g prime of some x value, and some x value in g is going to correspond to the y value in f. So these actually refer to the exact same number. Likewise, on the left, g of x is the input to f prime. So that's the y value in g. And over here, x is the input to f prime. So that's the x value in f. So it doesn't matter which way you go. And so going back to that slide I had earlier, the derivative of the inverse at some x value, so let's call this f, and let's just call this the inverse of f. Okay, so this is f prime of something, and this is the inverse of f prime at somewhere. So the derivative of the inverse at x equals c is the reciprocal of the derivative, is the reciprocal of the derivative at the corresponding x, which is f of c. Meaning, over here, if this c was, well, let's write out how I have it. 1 over f prime of f of c. Oh, gosh, I have that backwards. Well, let's do it with numbers. That wasn't great. Right. So here's what I'm saying. The inverse of f prime at 2 is equal to 1 over f prime of 1. Meaning, right, this 2 is my x value in the inverse. That 2 is the y value in the original function given. And so we want the slope, f prime, at the original 1, which is going to give the slope of the inverse at whatever this y value is, 2. Ooh, that wasn't great. We need some examples.